Hello, everyone. What I'm going to do now is define the Lebesgue integral for a general measurable non-negative function. I actually probably should have done that in the prior video, but it's okay. So quick review from last time. Let's say we have a bounded measurable function on a measurable set E that is non-negative. So we just let f of E be contained in this half open, half closed, half open interval. We partition the y-axis. So these sets here partition 0 to d. These sets right here. All right. So we set EI to be this inverse image. So these sets EI partition E pretty trivially. And we set this var phi n to be this function here. Okay. And if we do that, remember we have each of these is less than or equal to f of x, and they basically converge to f of x precisely point-wise for each x. And we graphically saw that the area under f of x on the set E for a nice function f graphically should be this sum here, which is according to our definition, which I'll review in a second, the definition of the integral of this non-negative simple function. Okay, and the idea is, I'm not going to spend much time here. So we, in a ton of detail, looked at the case n equals 4. All right. And I should mention that basically, y equals this black line, these black lines here, and these black lines here. That's going to be var phi n. We do have the endpoints to kind of consider. But basically, the gray area here is the area under var phi n. Okay? Or as we see here, so the purple area, the orange area, and the green area is the area under var phi n. So right here, this is going to be equal to, again, I probably should have put this on last video, but so let me get rid of this here. This one was 0 because there's 0 height in this red here. Y0 is 0. Right, so this whole thing here will equal the integral. In this case, it's n is 4. And by integral, I mean the Lebesgue integral. We're defining the Lebesgue integral to be this sum. Okay. And as n gets bigger and bigger and bigger, we get a better and better approximation of my function. We know that the var phi n's converge to f as n goes to infinity. So the area under these simple functions get better and better and better, approximating f. And the areas get closer and closer and closer graphically to what should be the area under the curve of f of x. Okay, so that leads us to the definition of the Lebesgue integral for a non-negative function. So let's say f is measurable, and theoretically you don't need measurability for this definition. It's just you really can't prove anything about the Lebesgue integral if you don't have measurability. And we're going to allow my function to be infinite value, no problem there. So let's assume this is measurable. E, of course, is measurable. So I'm going to define this integral as follows. All right. So I'm not just going to look at these approximating simple functions and then take the integrals of those. I mean, they would work, and you can prove, particularly using a combination, using basically the Lebesgue dominated convergence theorem, more or less. You can prove that, in fact, the limit of the integral of these var phi n's do converge to the definition I'm going to write down. But yeah, I don't want to just look at these as n goes to infinity. I want to do even better. Okay? I want to do as good as I can. What on earth do I mean by that? I'm going to take the supremum of all these approximating integrals, where I'm looking, the supremum is over all non-negative simple functions that are less than or equal to f. Okay? And the idea is that we know that we can find these simple functions converging to f, and hence the integral should converge to the actual area under the curve. That's the whole content of the simple approximation theorem. Okay. But we also basically proved that last time, and here's a quick proof. So yeah, so we did last time, and in the video on the simple approximation lemma theorem, that this simple function is always less than or equal to f. And if you forget how to do this, it's easy, very easy exercise, proving that pointwise the limit equals f. So there are always simple functions, non-negative. So I should mention these certainly are non-negative, these simple functions. Right, these simple functions right here are pretty trivially non-negative. Really nothing to it, because each of the yi's is non-negative. Right. So yeah, we certainly do have. There always exists a sequence of non-negative simple functions less than or equal to my original function that converges to my original function. And hence, all these areas should converge to the area under the function. Graphically, for a nice function, it's reasonable that it will. But why just stop at that? Let's just do the best. Let's just kind of do even better, possibly, than these simple functions. Okay? So yeah, this should be, so you should really think the supremum, remember the supremum is sort of like a maximum, even though the maximum kind of might not exist. So like, for example, like the supremum of the open interval 0 to 1 is 1. 0 to 1 does not have a maximum element. It simply doesn't. But in some sense, kind of 1 is like it should sort of be the maximum. You can get arbitrarily close to 1, but it's just 1 isn't in it, so it's sort of like it's like what should be the maximum if it existed, if it was actually in our set. Okay, so one kind of funky thing about this definition is that we now kind of have 2 definitions for a simple function. We will resolve that. Don't know if we'll do it in this video, but we will resolve that. Okay? So let me just remind you of the definition of the integral of a non-negative simple function. So let's say we have a non-negative simple function. It could spit out infinities here. That's fine. We simply define the integral of a non-negative simple function to be this sum where the yi's and ei's come from the canonical decomposition of my simple function. So this is the distinct image, elements of the image of my simple function defined over E. So take the inverse image of each of these distinct image points so that you can check trivially that we can write my simple function in this way, in the canonical decomposition way over E. Right? And it just so happens, this is very convenient, that if we have this, that E is partitioned by these EIs. Right? And so the integral is just going to be this sum here, as it kind of has to be, because the integral really should be linear. We'll prove that in this video. And the integral of each characteristic function should just be, well, the measure of that set. Just graphically, if E is an interval, then the measure of E is the area under the characteristic function. It's 1 times, the length of this interval. So this kind of should make sense. Okay? But what should also make sense is writing my simple function any other in any other way as a linear combination of characteristic functions, and it really just should be those coefficients times the measure of whatever sets we have. And we'll prove that is the case, at least for non-negative simple functions. And I mentioned you can define, you can, in theory, extend this to not necessarily non-negative simple functions. There just isn't a point. That'll get wrapped up when we talk about more general integration. So it's just, there's no point in straying away from non-negative simple functions. Okay, so yeah, so what I need to prove next, so the main thing to prove is linearity. Or in particular, that the integral of the sum of 2 characteristic functions is the integral, or the sum of these integrals. That is really the key here. So that's going to be a bit tricky to do. So let's do that. And once we do that, then we can resolve very easily these 2 seemingly different definitions if f itself is a simple function. We'll be able to show that that these 2 definitions are if f is a simple function. Particularly the supremum definition and this definition. Okay. So what I want to prove now. I'm going to prove the following proposition. I'll probably take up the whole video, but that's fine. Okay, and yeah, this is a Well, anyway. So let's say I have a non-negative simple function written in the following way. I'm going to follow notation that Royden uses, because why not? No reason not to. So let's say I have a non-negative characteristic function, or sorry, non-negative simple function. So each AI is non-negative. We're assuming the AIs are measurable, so that we have a simple function, measurable. So this is almost the canonical decomposition, but not quite. So let's assume that E is the disjoint union of the AIs. So the claim is the integral. I'll explain the subtlety here if it's not clear. So the claim is that the integral is AI times the characteristic function, the sum, AI, sorry, times the measure of little AI times the measure of big AI. So what's the subtlety here, and why? What's the point? Well, let's say we have. So as an example, let's say, and I'll explicitly. It's kind of silly even to do this, but I'll explicitly write this out in its canonical decomposition. So let's say this is just characteristic function from 0 to 1. So the canonical decomposition is, let's say, yeah, so to be clear, and I should say, I'm thinking of this as a simple function on E. That should have said that before. Right. And so these are all going to be subsets of that. So in this case, let's say E is just a real one. Can't get simpler than that. Okay, so right, so technically the canonical decomposition is 0. So the image is 0 and 1. That's the image of this simple function. On 0 to 1, it's 1. Off of 0 to 1, it's 0. So R take away 0 to 1. And I'll write 1 in this way. Right, so the canonical decomposition so in this case, n is just 2. So y1 is 0, y1 is 1. Sorry, y1 is 0, y2 is 1. So in this case, this is y1, y2, and this is so this is e1, This is E2. Order doesn't matter really. So this could be Y2, E2. This could be Y1, E1. I mean, order has no, doesn't matter how I label these. It's the same sum. So that doesn't matter. Probably should have been clear before. What was I? Right. So this is the canonical. I'll put that even. Make it absolutely clear. Okay. So this is absolutely the canonical decomposition of my simple function. It's just a characteristic function in this case. Right. This is absolutely the canonical decomposition. Sorry, of our function. Or really the whole thing. It's not clear. It should be, but if it's not. Right, but we could also do something. So let me get rid of all this here. Crowded. We could also do something just kind of stupid, and it really has no point except to, I guess, illustrate the point of this little proposition here. I could also write this characteristic function as let's say I equals 1, I don't know, the 10 of characteristic function. Let's say, yeah, so let's before I do that. Yeah, so 0. Or let's forget about, I don't even want to write it. Let's write, I don't want to bother writing the 0. So let's say I write it like this. I guess I'll still emphasize 0 times this characteristic function. Yeah, so let's say j equals 1 to 10, characteristic function of, I don't know, j, let's go to 0 to 10. Sorry, I'll do 1. So j minus 1 over 10. So like 0 to 1/10, 1/10 to 2/10, et cetera, et cetera. One. And technically, 1 here, but one, and this is a j. Right, right. So technically to get the endpoint 1 here, I just need another characteristic function. Right, so what's the point? The point here is I have my characteristic function written where I have 12 of these AIs. I have 12 sets here, 1, 10 sets here, another set here. So in this case, yeah, I have 12 A's, but they're not, but there's repeats. And we have 10 repeats. We have, well, actually, sorry, we have 11 repeats. We have 0 not repeated, but here I have 11 repeats here. Okay. So this sum here can be pretty. I mean, the claim is that this sum here is also equal to the integral, which by definition is this sum here, where we have the canonical decomposition. So in other words, by definition, right, so by definition, so this is, well, it's just, this is the canonical decomposition, so it's 0 times the measure of this, which we define, as we mentioned before, as 0 plus 1 times the measure of 0, 1, or 1. Okay. So in this case, if we do the same thing here, we're going to add up 1/10 10 times, which is also 1. So it'd be 0 times the measure of r take away 0 to 1, plus 1 times the measure of the singleton 1. They're both 0 by definition, and by the fact that the measure of the singleton is 0. Then you add up 1/10 10 times to get 1. The claim is that this happens in general, even if we have repeats, even if the AIs are repeated many, many, many times, this is still going to be true. Okay, so that's kind of the point. The point is to cover situations like this. And to be clear here, we do have a partition of my real line. So these 11 sets here, these 10 sets here partition 0 to 1 closed open, and add the singleton 1, we get 0 to 1 closed. Well, this is r takeaway 0 to 1. So this partitions the real line. So as long as we partition our set, we can have as many repeats as we want, and still the integral is going to be as you would expect it to be. Okay, so yeah, let's prove this little proposition. Second. So yeah, let's write the image of E, and kind of like in its canonical decomposition, y1 through yn. All right. And I'm going to switch to J here for my canonical decomposition. So again, just to remind you, these are distinct. Non-negative numbers. Could be infinity, that's fine. They're certainly non-negative. All right, so write EJ as the inverse image of YJ. Okay. So yeah, this has a nice little combinatorial flavor. I will leave some of the details as an exercise simply because I assigned this exercise for my class, and I'll probably forget to delete it. It's a good exercise. It's very easy. But okay, so for J, some integer between 1 and n, we're going to let IJ be the following set. So the set of all I in 1 to m, where AI is YJ. All right. So what's the point? The point is when I write this here, assuming each AI is not empty, which as I said before in a little text overlay, we're assuming each one is not empty. Each AI is in the image of var_phi, a simple function, just because it's right here. Right? Plug in any x in AI, it spits out little ai. Okay, so that means for each AI is one of these y's. Okay. So we're saying for each yj, pick all the I where AI is going to be that yj. Okay, so here are two claims. These are easy to prove. And as I mentioned, we're leaving these as an exercise. I'll do this as an example in a minute. For the example, or I'll explain these in the example we have already done. So the claim is that the ij is partition 1 through m. Right. Okay, yeah, so for example, here, all right, so there's only two yj's here, just y1, so I'll just remind you, this is going to be, sorry. This is y1, this is y2, okay. Okay, right, so here, I'll do this in red. I1, what is I1? I1 is all the little i's where AI is, in this case, 0. Okay, so when is AI 0? Well, it's just simply 1. Okay, because this here is a 1. This is A2 all the way through A11, and this is A12. Okay. So I2 is a set of all I where AI is equal to 1. Well, here we have 11 of them. So this is 1 through 12. Sorry, 2 through 12. 2 through 12. 2 through 12. Not 1, 2. Okay. So in this example, this is fairly trivial. The integers 1 through 12 are partitioned by I1 disjoint union I2. Right? And the reason why these are disjoint is very simply because these are distinct. Right? Okay, 2. And I'll again illustrate this in the example second. For each j from 1 to n, ej is going to be the disjoint union of the AIs for I and big I, j. Okay. Right, so I'll do this maybe in blue. Okay, so right. Sorry, I thought that was blue. Okay, so this is E1, 2. Okay, so yeah, E1 is this disjoint union. I'll explicitly write what this is in a second. Okay, well, there's only one element in I1, so this is just going to be a, sorry, this is AI. those just A1, and A1 is this right here. So this is A2 through A11, and this is A12. Well, this is just yeah, R takeaway 0, 1. And E2 here is this disjoint union I in I2 AI. So this is J, I'm sorry, I equals 2 to 12. So I'll do 2 to 11 and then 12 second. So yeah, what is these AIs? It's just I minus 1 over 10 to I over 10. Right. And so remember this disjoint union is sorry. This is going to be 1 to 12. Because these sets from I equals 1, sorry, I equals 1 to 10, these sets from I equals 1 to 10 are big A2 through big A11. And this is going to give me closed 0, open 1. So disjoint union 1. Right? Yeah, and so to be clear, this is 0 to 1. So yeah. So kind of trivially verifying it in this example. Okay, what this is saying is, in general, this is always going to be true. Okay. So self some more room. All right. So yeah, and if you have any questions, put comments on the video, and I could probably help you out. Okay, so with these two, if you have any questions on proving these, I can help you out. But these are really, if you're taking a course in measure theory, you really should be able to do this. Okay, so using 1 and 2, it's easiest to sorry, I have it up here. I have it here. Right, so it's easiest to work with this sum here. Okay, so I'm going to work with this sum here. And I'm going to, well, we'll see what happens in a minute. Okay. So if true, both 1 and 2. I'll explain when I'm using 1 and 2. So this here, ugly. So this sum here, I equals 1 to m, ai measure of m I. Okay, so because of 1, I can write this sum as a sum j equals 1 to n. I is in big I of j. Okay. If you have any doubts about why 1 implies that, well then, just that is literally what 1 is saying. It's saying to capture every I between 1 and m, we need to take the sum of j equals 1 to n, or if we're summing up over I is 1 to m, we need to sum up over j equals 1 to n, and then sum up I is in ij. That's exactly what 1 is saying. So j equals 1 to n. Okay, well, by definition, AI is Yj. So, yeah, so by definition, I should say, by one, by definition, this is Yj. So I'm going to bring it outside of the sum. This is sum over I for a fixed j. So I can do that as constant. Now by two, each ej is a disjoint union of the AIs. This is a finite disjoint union. So this is by two. This is j equals 1 to n, and you can see where this is going. Yj m of ej. Well, that's the proof. I mean, that's it. So again, if I'm not being clear here, this whole thing is equal to, for each j, the measure of ej. That's exactly what 2 is saying. Take the measure of both sides. The measure of ej is a sum I is in big IJ of A. Okay. So yeah, that's it. By definition, this is the definition. Remember that the YJs, because these are distinct, these this is this is basically they come from the canonical decomposition of my simple function var5. So because the YJs come and the EJs come from the canonical decomposition, this is the definition of the integral of my simple function over E. All right, so in the next video, we will see how this little proposition right here very easily relatively easily gives us linearity, which, as I said, is the key to really going forward in the theory of Lebesgue integration of non-negative functions. It's one of the trickier things to prove. All right. So actually, the way we're doing things, probably the trickiest thing to prove is going to be Fatou's lemma. But it's a really nice proof. It's a really nice proof, but that'll come later. All right, so long. Take care. Bye-bye.